This begins the Chapter 9 PowerPoint, all about air masses and weather fronts. In fact, if we just go to the first slide, that would be more helpful. This is a nice cover photo from the beginning of Chapter 9, and it shows an approaching weather front in Rainbow in western Iowa in June 2009. This chapter, which is divided into two PowerPoints, A and B, will cover air masses and fronts. Doesn't seem like a lot of material, but these are complex concepts which do need some elaboration. So once again to the next slide, an air mass is an extremely large body of air. In that blob of air, which could be several thousand kilometers in size and a few kilometers high, the properties of temperature and humidity are fairly similar in any horizontal direction in that air mass at any given altitude. Where do air masses come from? They come from what we call source regions. Those are areas that are generally flat, like oceans or plateaus, and of pretty uniform composition with light surface winds, so that if a blob of air sits over a source region for a long period of time, that blob of air begins to take on the characteristics of that source region. Now, the air masses that affect North America are grouped into particular categories based on the source region. The table, which is shown 9.1, shows the classification and characteristics of the 5 air masses that affect North America, which include continental Arctic, continental polar, continental tropical, maritime polar, and maritime tropical. This next slide, which is figure 9.2, shows the air masses that affect North America and their source regions. Obviously, the cold, dry air masses are continental Arctic and continental polar. They come from Canada and interior Alaska and the North Pole. Maritime polar comes from either side of North America over the ocean, the Northeast Pacific or the Northwest Atlantic Ocean and the maritime provinces of Canada. Maritime tropical primarily comes from the Gulf of Mexico and secondarily the Caribbean Sea and the Western Atlantic Ocean, and also thirdly from the Eastern Tropical Pacific. Continental tropical is the only air mass that we find on the North American weather map in summer only. Let's talk about the cold, dry air masses first. Continental polar and continental Arctic, CP and CA air masses for short. They originate over northern Canada and interior Alaska. The continental Arctic is somewhat colder than the continental polar, if you can imagine that. That comes in essentially the Arctic Ocean, the North Pole. Long, clear nights allow for strong radiational cooling on the surface because of the fact that there's a lot of ice and snow on the ground. That certainly adds a lot of coldness to the lower layer of the atmosphere because of all that solar radiation that came in during the day radiating outward at night. And of course, once you're north of the Arctic Circle, between mid-September and mid-March, they've got 6 months of darkness. Very cold and dry air masses. The dew points can go down to minus 30 Celsius, if you can believe that. The winds in the upper atmosphere cause a portion of these air masses to break away and plunge southward toward the North American continent. And there aren't any topographical barriers like major mountain ranges that run east-west or west-east to keep those air masses from moving southward from Canada and interior Alaska. The graphic at right, 9.3, shows a continental Arctic air mass originating over the Arctic Ocean in extreme northern Canada, shown plunging southward toward the U.S., and the leading edge of that is marked by a cold front. You can see the temperature contrast there. These are obviously temperatures in degrees Fahrenheit. 55 degrees Fahrenheit ahead of the front, minus 20 Fahrenheit behind it. Gee, I'll bet a cold front went through. What do you think? Now, if continental polar and continental Arctic air masses get into the deep southern United States, or even here in the West, they can cause extensive agricultural damage, as you can imagine. We had that cold snap here in January, which put in peril the citrus crop here in the Central Valley. If they move over relatively warm water, meaning the Great Lakes, they can cause those tremendous lake effect snows on the leeward side of the lakes that we covered way back in Chapter 5. Now, ordinarily, with these extremely cold outbreaks, the Rockies, the Cascades, and the Sierra Nevada tend to protect that bitterly cold air from reaching California and the western states, but there are exceptions. There was a cold air outbreak in 1989 in December that did manage to stay east of the Rockies. That was the U.S. West Coast dodging a bullet. But in December 1990, it was a different story. Continental Arctic air went right into California, and that's when, in December of 1990, Fresno Air Terminal tied its record low for any day in December of 18 degrees Fahrenheit there was extensive damage to the citrus crop here in December of 1990. Of course, in January 2013, we had another scare with continental Arctic air breaking into the region. Here's a kind of a case study of another extremely cold weather outbreak. Extremely strong surface high pressure associated with continental Arctic air dropped down into the north central United States, eastern Montana specifically, from south central Canada, bringing with it bitterly cold temperatures, and you can see how that stationary front is kind of draped across the southwestern U.S., which was essentially the dividing line between that Arctic air mass that affected almost the entire lower 48 states, except for Arizona, California, and southern Nevada. This is the surface weather map from December 24th, 1983. And the next day, December 25th, 1983, 125 record low temperatures were established in 24 states. It was quite an outbreak. In the summertime, the source regions for continental Arctic and continental polar air do experience longer daylight hours, even though the sun angle is low, and the snow melts. So what happens is that the air mass is modified. It's not as cold as it is in winter. So we don't see those CA and CP air masses plunging southward in the summertime in the U.S. very often. But when they do, they can certainly give the central and eastern United States east of the Rockies relief from any summer heat waves that might develop. Whenever you get a continental polar air mass that goes from the United States over the Gulf of Mexico or over the western Atlantic, you get a cloud pattern like this. This tells meteorologists, when they see a cloud pattern like this, that the temperature of the air is much colder than the temperature of the water's surface that it's moving over. So you get a tremendous amount of moisture sucked into that cold, dry air mass, which produces condensation and convection with showers as this cold, dry air mass moves over much warmer water. That would be the case for any season anywhere if this occurred. Now, we're switching gears to talk about moist, cold air masses, maritime polar air masses. These are the ones that frequently affect California in the winter and early spring, the ones we depend on to get all that snow in the Sierra that we certainly rely on when it melts into the reservoirs. In the wintertime, continental polar and continental Arctic air, CP and CA air, have their origins over northern Asia and Russia. Those air masses, which are cold and dry and stable, are carried eastward over toward the North Pacific Ocean, i.e. the Gulf of Alaska. And then that air mass, or those air masses, are modified with warmth and moisture, causing the air mass no longer to be bitterly cold, dry, and stable, but now becoming cool, moist, and unstable, and the genesis for major winter storms that come into the west coast of the U.S. in winter, which gives us the showers and snow and thunderstorms we experience generally, say, between November and March or so. The ocean's effect then is to keep the surface air warmer than the air aloft, and that destabilizes the air. As maritime polar air moves eastward across the western United States, the moisture is, of course, squeezed out on the windward side of the mountains, and then it's dry on the leeward side of the mountains. And you can see the schematic there in the northern U.S. with the Olympic Mountains, the Cascades, going across the high desert of Washington and Idaho, then over the Rockies, and then that air gets modified as it goes east of the Rockies and becomes continental polar air, but not nearly as cold as the continental polar air that drops southward from Canada. No question about that. Maritime polar air masses on the east coast are kind of rare because, as you learned in previous chapters, the winds above our heads in North America, called the westerlies, move from west to east, and that tends to push maritime polar air out over the Atlantic Ocean. But sometimes, if the weather pattern is right, if the winds are in the right position, maritime polar air from the western Atlantic or off the east coast of Canada can move into the northern United States and really juice up the atmosphere and cause a lot of precipitation like rain and freezing rain and snow and so on, and can also be instrumental in producing the kinds of storms called nor'easters, which sometimes hit the east coast in the winter and springtime. The figure 9.9 at the right shows a typical winter and early spring surface weather pattern in the eastern U.S. with maritime polar air coming in from the Canadian maritime provinces into New England. Maritime tropical air. This is a warm, moist, and unstable air mass. It originates, of course, in warmer waters like the western tropical Atlantic, the Gulf of Mexico, the Caribbean Sea, and to some extent the southern part of the northern Pacific, north of the equator. When maritime tropical air affects the west coast in winter, it can cause storms with very high snow levels, which melt the snow that's already on the ground. And this is the so-called Pineapple Connection or Pineapple Express. No, it's not that silly movie you streamed on Netflix, and you know what I'm talking about. This is an infrared satellite image from January 1st, 1997, showing this so-called Pineapple Connection, with very warm, moist air causing a tremendous amount of rain that fell on snow that already was in the Sierra, rather deep snow that fell in December of '96, just the month before. And the snow level then went up to 10,000 feet. This caused a lot of flooding along the primary floodplain of the San Joaquin River at that time, right near Fresno and Madera counties. Additionally, there was a tremendous amount of flooding in Yosemite Valley. You can look at this hyperlink on your own to see the National Park Service video of flooding in Yosemite Valley during this episode. It's quite dramatic. You'll want to take a look at it. Now, maritime tropical air is a lot more common on the East Coast and can be the source for early season heat waves. Note the 96 up there in Massachusetts. This was in April of 1976. And note on the opposite side of the country, continental polar air was invading, which even caused some very chilly temperatures along the central and southern California coast right around this time in mid-April of 1976. So you can have one air mass of completely differing characteristics on one side of our continental U.S. and one which is quite different on the other side. Maritime tropical causing early season heat waves on the East Coast. Maritime tropical air can sometimes come up from the Gulf of California and be lifted by the nearby Sierra Nevada and cause those towering clouds and thunderstorms that we sometimes can see over the crest of the Sierra to the east of us here in the valley in the summertime. Now let's get to the hot, dry air masses. Continental tropical. This is the one that causes our heat waves, especially in the southern and southwestern U.S. in the summertime. Figure 9.14 to the right shows maximum temperatures that were recorded as a continental tropical air mass dominated the southwest U.S. between July 14th and July 22nd, 2005. Note the 125 at Needles, California during that period. These are hot, dry blobs of air that are conditionally unstable. If they do lift high enough, they can produce thunderstorms if there's moisture present, but mostly they're just hot and dry and are the major source of heat waves over the southwestern and southern U.S. In the summer. If one of those migrates southward over toward Texas, Oklahoma, or even into the Central Plains, goes more eastward than it typically does, then this can be a source of persistent heat and drought in the central and southern plains. And that occurred in the summer and fall of 2012, the year just passed. This is a case study of continental tropical air in the July 2006 heat wave over the southwestern United States. It's quite an astounding heat wave, and it had a major effect on Fresno and the valley here. Record-breaking heat occurred because of this hot, dry continental tropical air mass between July 22nd and July 26th of 2006. High temperature records were set in Fresno on the first of those 4 days, first 4 of those 5 days, I should say, with 112, 113, 113, and 113 respectively. Those were the high temperatures on the 22nd, 23rd, 24th, and 25th of July, 4 consecutive days. On the 26th of July, the 5th day of that heat wave, the high of 112 in Fresno missed, tying a record, a daily record for that date by 1 degree Fahrenheit. On the 23rd of July, it was a Sunday, the low temperature was 90 in Fresno, which was the highest low temperature ever reported on any day in Fresno weather recorded history, if you can imagine that. So the low and high on the 23rd of July was 90 and 113. This map is courtesy of Plymouth State University, New Hampshire, which shows a 5,970 meter height contour right there in the center of that tremendous high pressure aloft, the continental tropical air that caused a heat wave that the National Weather Service reports almost 50 people died in Fresno County alone from that valley heat wave. This concludes the PowerPoint for Chapter 9A.